Professor Constantinos Vayenas, it's a pleasure to have you here. It's an honor. I followed one of your presentations and I was impressed. First, for your passion. Not too many university professors, present in such a passion their subjects. That was something that impressed me. Can you have about 40 years as an academic and as a professor. Can you make a resume of your achievement, something that you are proud of during all these 40 years in universities?
Yeah, I have worked in several fields. I enjoyed very much the years I was working in catalysis and electrochemistry. That's why the National Academy of Engineering of the United States honored me last year by making me a foreign member of NAE. That was the first Greek scientist to become a foreign member, and it was due to my work in catalysis, on using electrochemistry to make better catalysts, which are also used in industry. The second achievement about which I'm proud is what we have recently done in high energy physics. This is a different field, of course. However, there are many similarities, which I pointed out yesterday, between chemical physics, which is what I've been doing for 40 years, and high energy physics, what I've been doing for the last 12 years. So basically, what we have done in high energy physics is we have combined special relativity of Einstein with the law of gravitation of Newton and with the basis of quantum mechanics, which is the de Broglie equation. This is our model, just combining three very well-established equations and developed in this way a model which enables us to compute with an accuracy better than 1% the masses of all the composite particles, which include the proton, the neutron, on the basis of just the natural constants, nothing else. There is no unknown parameter in our model. We only need to have the mass of neutrinos, which is a key element of our model. So what we find is that these composite particles, like the proton and the neutron, consist of neutrinos, very fast neutrinos, relativistic neutrinos, which behave as quarks. You've probably heard that protons contain 3 quarks. Well, according to our model, you find that these quarks are relativistic neutrinos, which are running very fast on the basis of the gravitational attraction. So what we have found is that, surprisingly, the strong force is relativistic gravity, described by Newton's gravitational law and Einstein's special relativity.
To make it a little bit understandable for general public that are not scientists like we are, what are possible applications of these achievements?
Okay, first a better understanding of nature. So far we're taught even at elementary school that there are 4 forces: electrostatics, gravity, the strong force, which keeps the protons and neutrons together, and the weak force, which again keeps some of these elementary particles together. And what we have found now is that both the strong force and the weak force are relativistic gravity. The strong force is a relativistic gravity between neutrinos, and the weak force is a relativistic gravity between fast electrons and neutrinos. So we know now that we have only 2 forces in our nature, in our universe to take account of: gravity and electrostatics. In the very long run, you could envision practical applications for energy production, because the basic thing we have found that it is neutrinos which are everywhere around us. Even in our body right now, as we're talking, there are 70 billion neutrinos crossing every square centimeter of our skin every second. So they're everywhere. So these neutrinos have combined in the past and form protons and neutrons. And this is a very exothermic reaction. What does exothermic mean? That energy is being released. So perhaps in the future we can harness this energy. This energy produces even bigger than what you have in hydrogen fusion. And perhaps we can find the means to harness it. And I think the probability is very high for this, and perhaps in a much safer way than, say, nuclear fusion or hydrogen fusion.
So it's a possibility to have a new kind of energy.
Absolutely.
Which would be sustainable.
Absolutely.
And also without waste.
without waste, because the only products of this are protons and neutrons. At CERN, even today, they can generate mass, they can generate some mesons in this way, in the so-called positron-electron annihilation experiments. So they co-feed the positron and electron in a vacuum, and they get annihilation of this pair with production of mesons, which are first cousins of proton and neutron, which are hadrons.
You mentioned Einstein, and you mentioned there is a special relativity theory and general relativity theory. Can you say a few words in simple terms for us?
Yeah. Special relativity was first developed by Einstein in 1905. He published a monumental paper. Special relativity is based on only two axioms. First of all, that no particle can move faster than the speed of light. And second, that all reference points in our universe are equivalent. All observers have the same right to describe things. So the first result of special relativity, which has been confirmed thousands of times by experiment, is the so-called space contraction and time dilation. Most people have heard the story about the two brothers, one leaves the Earth and returns after years. But these are very well-proven facts that for particles which move very fast in relation to us, we have a space contraction. We see that things far away get closer together, and a time dilation. We see that things take place slower than the observer there sees. And out of these observations, out of these two facts, comes the fact that fast-moving particles have bigger mass. As a particle gets faster and faster and approaches the speed of light, its mass gets bigger and bigger. So this is the essence of our model, in the sense that all this is described by special relativity, and the particles which we find in our model, 3 neutrinos, rotate around, are very fast, and therefore the gravity between them enables them to stay and form a stable structure. So special relativity is a necessary extension of Newtonian mechanics. There's no doubt about this. It has been confirmed thousands of times. Even the nuclear bombs are a manifestation of special relativity. Now, on the other hand, general relativity is an ingenious idea of Einstein, formulated 10 years later. But it is a theory of gravity, the most successful theory of gravity, but there are 40 of them, okay? So we cannot say that it is as well tested as special relativity. Special relativity is inevitable. General relativity is a theory. It does very well at the relatively low velocities of celestial bodies, you know. But here with these particles, we're talking about extremely fast particles, moving very close to the speed of light. We have done preliminary calculations showing that general relativity also can describe the force we find, you know.
So by combining these three equations, you are coming up with a new discovery, new explanation of phenomena?
Sure. With these three equations, let me clarify. We have developed no new theory. We have just combined three well-established equations of physics. Newton's gravitational law, Einstein's special relativity, and de Broglie's equation, which is the basis of quantum mechanics. So it's a model what we have. We have put together three very well-established facts. We have developed no new theory. And our model contains no adjustable parameters. And this model enables us to calculate with an accuracy better than 1% the masses of all the composite particles, the proton, the neutron, the various mesons, etc. So this is essentially what we have done. And we were very lucky because for the first time we have used Newton's gravitational equation using relativistic masses, using gravitational masses first developed by Einstein in 1905.
So Einstein is famous for relativity, but his discoveries also are relative, I guess. Exactly. So in different conditions there are different laws, different. Can a theory be so general without exceptions?
Absolutely. Special relativity is such a theory. You see, I was an engineer to start with, and in engineering, practically every equation we use has its limitations. It can be valid for 5, 10 orders of magnitude, But what happens in physics with the Einstein equation that we all know, namely that energy of a particle is gamma, the Lorentz factor times rest mass times c squared, it's amazing. It's valid over at least 60 orders of magnitude. This is what we have found, and I was extremely surprised. This equation is intimately related to the world in which we live. It's not human-made. It's made by nature. Okay, so it holds over 60 orders of magnitude. This equation of Einstein.
You are reformulating by combining three equations, the theory of Einstein and other Newton and the Bray. Now, after 40 years of career, so have you thought before that you're going to end up with discussing about redefining and combining equation of Einstein, etc., etc.?
No.
How it became possible?
It became possible in the following way. As I told you, I'm also an electrochemist, and we were studying the conductivity of naphthalene, which is a key component of fuel cells, power generating devices. And there we found, and we confirmed actually with isotopes, that part of this conductivity is due to the tunneling of protons. So protons, with very small particles, travel in these membranes, both behaving as particles and behaving also as a wave. Okay, so this was my first introduction in understanding what tunneling is, It's the motion of a particle in the form of a wave. Okay, and this gradually made me very interested in physics and studying more and more of it. And the second thing was a thought that perhaps a high school kid can easily make. This Einstein equation with E equal gamma and not c squared. Gamma can go to infinity as the velocity of a particle goes to c, the speed of light. So I said, well, if we have some particles which for some reason move very fast, close to the speed of light, their mass becomes enormous. And maybe the gravitational attraction between these particles is what we call the strong force. So this is what made me very interested in this. And after a couple of years, I had already formulated the two very simple equations, which, as we discussed, is Newton's gravitational law plus Einstein's special relativity, which amazingly was giving us the correct mass for the proton. Starting from 3 neutrinos, which have a mass, the three of them, which is 10 billion times smaller than the mass of the proton. But from Einstein's equation, it follows directly that if they're rotating so fast, and they are, due to the gravitational attraction, then they form the proton.
Who made you interested in science? Was your first choice when you were a child?
Absolutely. I wanted to, for those days, to understand astronomy. Maybe I was very fortunate because I was only 7 years old, and someone, I cannot remember exactly who, gave me as a gift a small...
At what age?
7 years old. 7 years old. A book about astronomy, explaining what the planets are and all these things. And, well, it made me very interested because, I realized that many of the things that were described there were not in direct agreement with what we were taught, about how our world was made, etc. I gradually understood that, maybe there is no big conflict between the two. It's another question about this. So this made me very interested in science. I learned already when I was 7 what the planets are, what their names are, what the galaxy is, all these things. So,
and this was in Greece?
This was in Greece, yeah.
Yeah, and you never thought going to another profession like law, never crossed your mind?
No, never. Although I was very fascinated by ancient Greek. I liked languages a lot. They say that if you're good in mathematics, I was decent in mathematics, then you're good also in learning languages like ancient Greek, because there are rules there, very well established rules in this language. And so I liked also ancient Greek, I liked learning new languages, and I'm fascinated by this. That's always my heart was in science, yeah.
And if you go back 40 years, would you have chosen the same profession?
Yes. Many people ask me and say, Kostas, what a pity you didn't study physics from the beginning. I must say, I'm proud I became a chemical engineer because it's a very versatile education and you are free in your mind. You haven't been taught about quarks and QCD, etc. You are more free in your mind. So when you try then to get into physics at the age of 40, as I did, you go to the roots, you go to read Einstein, you go to read Newton, you know. And this gives you the possibility to think through this great.
But still we are in the domain of science. So science, physics and engineering.
Very closely related.
But you would not have chosen another profession if we go back in 40 years, like law, like sociology.
No, I'm not made for this. I'm not made.
Because?
Because, you know, I was good in math, I was eager to learn about our universe, about our world. I admire people who can be good lawyers, you know, and there are many examples of this in the history of old Greece, you know. But my inclination was always in science and mathematics, you know.
So then you went to United States?
I went to the United States.
At what age?
I was 23, and there I did my PhD at the University of Rochester. I was very lucky because I was asked by my professor, Professor Salzburg, to work in an area which was combining electrochemistry and catalysis. This is what I did for my next 40 years, and I'm still doing, you know, maybe 30% of my time. Then I was fortunate, I was hired as an assistant professor at Yale. I taught there for a year, I have very, very good recollections from this. Then I was fortunate, I was invited by MIT to join there as an assistant and then associate professor. I spent 4 amazing years there. Then, for family reasons, I returned to Greece, but it was also challenging scientifically because this was a new department which was being created.
Where? In MIT?
No, in Patras.
In Patras.
And so they attracted 3 of us, Greek professors from the United States, and gradually we made this a good department. Believe it or not, it was ranking 2nd in Europe 10 years later and 14th in the world. So we had done a good job. Then we had my chairman from MIT, Professor Jimmy Way, visiting us and saying to me, Constantinos, you are doing a great job here, but I don't see the steady state. I don't see how you can sustain this high level of quality in the long run. And he was right, you know, because the economy of the country became weaker over the years, so this is the reason we cannot say we're as strong as we used to be, but we still try hard, you know.
And the reason for returning?
To Greece? I told you it's family considerations, a love to my parents, my grandparents, love for the landscape perhaps. But America is like my second home, really. When I'm in Boston, I feel I'm at home, you know. So I really very, very close. Last year when I went back to the East Coast in Boston, I had tears in my eyes. I spent there a good part of my life, and it's home for me as much as Greece is, you know. And I still have very good friends there.
And you go back and forth?
As often as I can, yeah, sure. Once every year I go, I try to go.
And what's your hobby besides science?
Well, chess and watching athletics and football and basketball.
So you play football, basketball?
I watch. I used to play.
You watch? You used to play?
Yeah, I used to high jump in my youth. That's a long time ago, yeah.
No, just interesting. So you used to high jump?
Yeah, I was a member of the Greek youth national team for a couple of years.
Oh, really? National team?
Yeah. It's youth, I don't know. Yeah. This was before the phosphor flop was invented.
And why you didn't become professional athlete?
No, well, I was also...
So they are very well paid, much more than the scientists.
Yeah. But, you know, I was not as tall as necessary for this. Then 2 other Greek guys appeared, which could jump 20 centimeters more than I. So I couldn't be on the national team anymore. I had to study hard in the Technical University of Athens. So there was no time for this. But it was something, you know, being an athlete is something which helps you in your whole life, not only in terms of health, but in terms of establishing goals in your life and trying to reach them, you know. This is what I learned from athletics.
How long you used to high jump?
3 years.
3 years?
From age 15 to age 18, yeah.
Wow, and you didn't follow the professional?
It was not professional. And, you know, in athletics in Greece, it's never really officially professional, okay? Nobody's paying, even our Olympic winners, you know, directly. Okay, they have a lot of indirect benefits, but in athletics, you know, this is something really sacred for the Greeks, you know. They have to keep the amateur tradition, you know. Football players and basketball players, of course, a different thing. So the athletes, the track and field athletes also are reasonably rich, but not by direct payment, by gifts, by a lot of
Sponsorship.
sponsors, exactly.
Sponsorship.
Exactly.
But there's a question. So how many scientists are sponsored at the same amount like sportists?
Very few. Very few. But look, you can be a scientist for 40, 50 years. You cannot be an athlete for 40, 50 years. So it's reasonable that these guys can make much more money per year. In the long run, maybe we average the same. Who knows? Not the top one, not the top, say, tennis player or basketball player in the world. When I was at MIT, my salary was maybe 40,000 per year, and Larry Bird was making a contract of $2 million at the same time.
And how you feel when you hear that?
I admired him. He was one of my idols. So I said, okay, he deserves it. And he cannot play this level of basketball for more than 10, 15 more years. So he better make some good money now.
Yeah.
And what about your children?
Oh, I'm proud of them. I have 4 of them, and 3 daughters and a son, and now I have 2 granddaughters, one of my daughters, and my son.
What professions are?
Well, the eldest Julia is a musician. She plays the piano. She teaches piano, artist. The second, Vasya, is a teacher in elementary school, and she likes it a lot. George Philip, my third child, is going to enter hopefully the Greek university this year.
It was Phil.
It's Phil. Well, until last year he was telling us physics, but this year he tells us chemical engineering. So, okay, so
And the fourth?
The fourth, Anna, we are not sure yet. I think she wants to become a psychologist. We will see.
So among 4 children, only one is going to science.
True, yeah.
That's how things have changed since the 60s.
They have changed a lot, that's for sure. Furthermore, they see some of the disadvantages of having a parent or 2 parents working in science, because we have to work hard, because it's our hobby also, we like it. So maybe we don't spend as much time at home as we should. So this may be another reason they are not eager to get into science. Who knows?
No, that's perfectly true. It's not only your opinion, but it's everybody's opinion. So is it an advantage? Is it a disadvantage? This is one of the reasons not too many people going to engineering and science in developed countries anymore.
Exactly.
This is one of the reasons.
Exactly.
So what we can do about that? So we are the less perceived by society, like in terms of quality of life and in terms of money making.
Exactly. Yeah, this is true. Things have changed a lot. Yeah, when I was a child, it was the dream of most children to become scientists.
We are speaking about 60s,
60s, even 70s.
70s, yeah.
It was the effort of humanity to reach the moon, as we did, a lot of things like this.
But how things change so drastically? What's your opinion?
Well, salaries, of course, are one thing. Well, we lost the scientists. We lost control somehow. People who were sponsoring us became gradually more powerful, at every level,
Powerful being?
Means that they're controlling, the funding, Government. I mean, to get our research going, we need money. We need to be able to support graduate students. We need to be able to buy instruments, most of us. And so we rely then on national funding agencies. We also rely on industry, And maybe industry now, in most fields, not so eager to support science. I mean, I say this in the area of catalysis. When I was in the 60s in the United States, the research teams of some of the big oil companies were as good as MIT or Stanford. I mean, they had excellent people, working in industry. Now this is not the case anymore. Maybe because today you cannot make as much money by making catalysts, as you could those days. Those days, the catalytic converter was first developed, actually by a good friend of mine, Louis Hegedus, of Hungarian origin, who unfortunately passed away. last year. So you could make a lot of money, industry could make a lot of money by protecting our environment. Now, thanks God, most of these problems have been to some extent solved. So the oil companies started having less and less support for fundamental research. That was one major reason. So you have now less talented people, less in number going in this direction. So everything is moving more into high tech.
High tech catalysis can be high tech.
Yeah, but in fields like mostly biochemistry, things like this now, biologists gaining much more importance. And you saw this in
Biologist.
biologists, right? Medicine, protecting the human body. Here we had a very excellent talk about aging, how we can avoid aging. It's amazing what people now are doing in biological.
Biological still are still paid well.
Some of them are, yeah.
So you're saying scientists lost in the last 30 years. How can you win back? Just to finalize.
By trying to become more useful to the society, by addressing the problems of environmental hazards that we have now, the global warming problem. Yeah, that's where we have to spend more attention, and there a lot of good science will be needed.
So you are optimistic, pessimistic, or in between?
In between. I had a good German friend who was telling me that if 5% of the German parliament knew the second law of thermodynamics, it would be a much safer world. I'm saying the same, of course, about the Greek parliament. There are very few politicians who understand something about science, who understand the dangers we have for our planet. That would be a great thing if we had more scientists in our parliaments, the people who really make the decisions. It would be a great thing.
Yeah, but not too many are there.
Exactly. It's difficult to combine both anymore. I don't know why, but we have less and less of them in parliaments. Yeah.
Okay, it's very interesting. We really appreciate your insight on all these issues. We really appreciate also that you are with us, and you had a very good, very good presentation, which I enjoyed. I enjoyed your passion, by the way, as I said in the beginning.
Thank you.
Thank you very much.
Thank you. Real pleasure.
Yeah, thank you.
Thank you.